Okay, welcome everybody to the High Performance Computing Workshop, sponsored by the Hawaii EPSCoR, the Change Hawaii Project, the National Science Foundation, the University of Hawaii Information Technology Services, Cyber Infrastructure Group, and the Hawaii Data Science Institute. So like to have David Schanzenbach and Olivia Jarvis introduce yourselves to everybody, and then feel free to take it away.
Click over to the presentation slides and I'll introduce myself. So hello, I'm David Schanzenbach. Title is Lead Software Architect for Cyber Infrastructure. Basically help manage the cluster. My co-presenter is...
Hi everyone, my name's Olivia. I'm a first-year grad student at UH Hilo, and I am one of the Hawaii Data Science Institute Fellows this year.
So as Sean said, we're going to be presenting the workshop on high performance computing. So let's just dive right in. So what is high performance computing? So things we want to answer in this section are basically what is it and what components make up an HPC system. So you might have heard words such as clouds or phrases such as clusters or high performance computing HPC are used in a lot of different contexts for various related meanings. So what exactly do they all mean? And more importantly, how do they relate to our work? So the cloud is usually a generic term commonly used to refer to computing resources that are provisioned by users on demand or represent real or virtual resources. They may be located anywhere on the earth. Oops, yeah, drop that link there. But so for example, a large company may have compute resources that are located in Brazil and Japan, but internally it's considered one large infrastructure cloud for their entire company to use. Some also use commercial clouds, such as the ones that Amazon or Google provide. Cloud resources may refer to machines performing heavily related simple tasks, such as serving websites, providing shared shared storage, providing web services, such as email or social media platforms, as well as more traditional computing-intensive tasks such as running simulations. The term HPC system, on the other hand, describes usually a standalone system or resources for computationally intensive workloads. They're typically comprised of multitude of integrated processing or storage elements designed to handle high volumes of data and/or large numbers of float point operations or flops with the highest possible performance. For example, all the machines on the top 500 list are HPC systems. So top 500 list is basically a list of high performance computing clusters that are around the world. They basically run a suite of benchmarks, and a couple times a year, basically they duke it out for who's the top of the world. And then, you get dethroned the next time around when someone builds a bigger, better cluster. But basically it's a list of the fastest machines in the world. To support these constraints, the HPC resource must exist in specific fixed locations. Only because, yep. Sorry.
Who's right now in the world?
I think is it the United States right now? Let's find out. Let's check out what the top 500 is currently. So,
is it the new Summit machine?
It might be at this point. Frontier is currently #1. This was the June list, I believe. So they do this around supercomputing, which is a conference that's run international supercomputing, I think supercomputing. So the new list will probably come out in the next month or two as to who's top of the world. But currently it's Frontier, which is located in Oak Ridge Lab in the United States. Yeah. And then Japan has #2.
Did you know Frontera was supposed to be named Frontier, and then they got in a fight with Oak Ridge?
Yeah. So basically it's large systems. The cluster at UH, Mana, doesn't even reach the top 500. So we are very small compared to these systems. But it is a list that basically is, as you said, generated multiple times a year. And it is worldwide. So US is sometimes the top, Japan gets the top, sometimes China, though I think China at this point probably doesn't release their fastest machines for the listing. So basically, HPC needs to sort of be in a fixed location because network cables can only go so far. Electrical and optical signals can only travel so fast. So really with a cluster, it's really a tightly coupled system where cable lengths and stuff at some point will start to matter, since you have all these machines trying to communicate over a network to each other, and you want the fastest speeds possible. So what else are HPC systems good for? Typically HPCs are meant, designed for large problems, or thought of in that way. But even smaller cases, such as you need a single server, or you have a research problem that has very short tasks, but you have a lot of them, like tens of thousands of them. So HPCs can do this other type of workload, or can also facilitate for this type called high throughput computing, which is really, you have a lot of independent jobs that you need to run in parallel because of time constraints. And because HPCs have so many resources involved with them, you can run a lot of jobs in parallel. So what actually makes up an HPC system? What are the components of an HPC system? So individual computers that compose a cluster are typically called nodes. Although you mostly refer to them as servers, computers, or just machines. On a cluster, there are different types of nodes that all have different types of tasks. So what makes up a node? A node in itself, in HPC system, are comprised of basically the same components you find in your laptop or your desktop. They comprise a CPU or a processor or cores. They have some type of memory or RAM, and they have some type of disk space for long-term or storage, basically. CPUs on computer's tools for any actual calculations or programs. Information about the current task is stored in RAM or memory. And the disk refers to all storage, basically like a file system. This general storage can hold data permanently. So basically, if you restart your computer or shut it down, you're able to retrieve it again without having to recalculate it. While storage can be local, like a hard drive in your machine, it's more common on nodes in a cluster to basically use a file system or a network file system to serve out the data. For instance, on Mana, a very few of our machines actually have hard drives in them. Most of the machines in Mana are actually diskless. So what happens is the operating system's pulled over the network at boot time and loaded into memory and runs in memory. So when you shut them down, basically it's wiped clean. It has to load the operating system again on reboot. So it's sort of a simple diagram of a machine. You have cores with some type of shared memory between them. So the processor, you have basically a bus that goes between the memory and that processor, and then you have disk that has some bus to the processor as well. Specialization of nodes that we mentioned. So there's things like login nodes. These servers are specialized, meant for accessing the cluster, the gateway to your cluster. So they basically facilitate small uploads and downloads of files, or basically submitting jobs to the cluster itself. There's data transfer nodes. These are typically delegated specifically for data transfer, as their name implies. So typically you want to don't want to obstruct the login nodes by doing long, large transfers. So you set up these machines that are meant for these type of transfers, and specifically, so large maybe files that are over 500 megabytes in size or up to a gigabyte in size. Typically it changes depending on the network connectivity of your cluster and your local machine, or whatever machine you're transferring to and from. On Mana, we actually do have 2 data transfer nodes that are currently available for use for this type of transfer setup. Compute nodes. So the compute nodes are really where the work on the cluster gets done. They're your workhorses of the cluster. Compute nodes come in many shapes and sizes, but they're generally dedicated to long, hard tasks and require a lot of computational resources. So different types of compute nodes you might have are just straight up CPU nodes, so they only have CPUs in them, and they're meant for computational resource jobs that use CPU only. They're nodes that have a lot of memory, so maybe your standard node only has 120 gigs of RAM, versus you have machines that have up to 1 terabyte or 3 terabytes or more of RAM available for use in one machine. You also have specialized processing units such as GPUs on certain machines. So if you're doing things that require GPUs for processing, such as machine learning or deep learning, there are these specialized type of compute nodes that have those type of processors in them. Interactions with all these compute nodes are done through a scheduler. In the case of Mono, we use what is fairly well established at this point in many clusters, a scheduler called Slurm Workload Manager, or just Slurm. It actually is a product that came out of one of the national labs. I forget which one actually at this point, probably over 20 years ago at this point, that went open source. And there's a company that supports at this point that spun out from those efforts. sort of supporting in the sense of development, things like that. And then we have the support nodes, which as a user, you never see, but they basically are what keep the cluster running. So they basically manage the hard drive or the storage of the system, user authentication, or all the infrastructure related tasks that administrators need to worry about more than users. If one of these goes bad, well, users experience bad experiences, and so they have to be maintained just as well as any other machine in the cluster. Any questions, I guess, about parts of a cluster, what difference between HPC or cloud computing, things like that, from anyone?
Is there a limit on the file size that can be stored on the data node? Max file size?
So on Mono, we don't really have a local scratch for storage. So basically, it's going to be based off of whatever the backend file systems are. So right now, as Mono is currently configured, if you own storage in the cluster, you could have access to whatever you purchased there, including whatever scratch spaces you have. So we have some disks that are fairly fast, some are a little slower, but the typical scratch space right now is 5 terabytes per scratch system we have access to. So it varies, but it's all network mounted currently, as far as that's concerned. Good question. Any other questions? Yes, I'll move on to the next session. So connecting to a remote HPC system. So in this case, questions we're looking at are, how do you log into remote HPC systems, and what is open on demand, and how do we use it? So connecting to a remote HPC system, the first step in using a cluster is establishing a connection from your laptop to the cluster. When we're setting up a computer or holding, however you want to, however you compute, maybe you like to hold it on one hand and type with the other. We have come to expect a visual display of icon widgets, so a graphical interface, a GUI. HPC systems, on the other hand, are typically connected over the network. So you're maybe connected via a slow or laggy interface, such as Wi-Fi or VPN or virtual private network. So graphical interfaces aren't usually practical on HPCs. So typically you have a command line interface or CLI that you're using. So if you attended last week's workshop where we went over the scientific basics command line, all those things are typical on a cluster. Learning how to use ls, make dir, move, and get, and things like that. So you can basically move your files around because the only text is transferred in a CLI. Anything else that's image-wise other than text, like images, would have to be written to disk and open as a separate program. So you may wonder, have you ever interfaced with the command line interface yourself before? So if you ever opened up a Windows command prompt or Mac's terminal or things like that, you have seen a command line. Windows is a little different than Mac OS, and Mac OS is most similar to Linux or FreeBSD, or what you'd see on a cluster, basically. But they're all command lines nonetheless. So basically, when you talking about the shell Unix one, so basically the scientific carpentry one that we did, the only leap you have to make with the CLI then at this point is you have to connect to a remote machine, while taking some precautions to make sure that other folks on the network can't snoop on what you're doing, basically. So these days, what typically is used is secure shell protocol, or SSH, to basically open an encrypted connection between two machines, allowing you to send and receive text data without worrying of prying eyes. So you can think of it as basically you have your laptop, travels to the internet, and gets to the cluster, and basically it's all an encrypted tunnel. So traffic is basically flowing back and forth without anyone being able to see it, other than you. Now, traditional access is using SSH. Most modern computers these days have SSH a client built into their terminal. So if you use something like Windows 10, Windows 11, Mac OS, any flavor of Linux, previously as I mentioned earlier, all of them have SSH on the command line. You can type SSH and it'll pop up a client that you can use. Alternative clients exist primarily for Windows, since Windows for the longest time did not have one built in. And then there's also add-ons these days to even your browser. So you can have SSH client in your Chrome browser if you want. But all these operate in a similar manner. It's usually a command line tool, so it provides remote access to machine addresses when required. Typically, you might have to provide also your username on that machine, so it may not match what your local machine's username is. So I'll skip this because these are mostly graphical about the Windows one. So there's Windows terminals that are called PuTTY or Moab External, which use a graphical interface to connect. But typically on the command line, the format is SSH space your username at the host name, where the at is basically the separator between the two arguments. We won't actually be using SSH today directly, so I'm going to skip over this particular activity since we're mainly going to focus on using Open on Demand for the activities we're doing today. So alternative to Open SSH, especially on Mana, is this thing called Open on Demand. There's many other tools that exist that sort of can facilitate this well, but we're using Open on Demand for this instance. So Open on Demand is actually a product that's and it's funded. It's actually out of the Ohio Community Center, and several places are actually collaborating on it. Basically, you can think of it as it's all in the browser and allows you to we sort of frame it as a way to bridge between going from the graphical interface down to command line interface. So basically, the middle ground between those two. So you can sort of have the flavor of both, while easing into using the command line more and more. So features of Open on Demand. Basically, as I said, it's a web-based thing. So basically, you just need a web browser. So pretty much any machine, your phone, whatever, can use Open on Demand to connect to the cluster. Has basic functionalities to basically file browse, upload and download files, text editing, even has an SSH terminal built into it. And also there's these things called interactive applications, such as remote desktops, Jupyter Lab, Jupyter Notebooks, or even RStudio. They also have multiple other applications that we don't currently have installed on Mana, but they do have a whole list of applications that you could actually install into your Open on Demand instance to actually use in these interactive apps. Things to note about using Open on Demand and the recommendations. So first off, it does require a modern browser. So if you use Chrome, Firefox, Edge, all those are pretty much well supported under Open on Demand. It has limited support for Safari. Mainly it has issues with some functionality, I think, in the terminals, if you're going to use an SSH terminal through it. But for the most part, it'll work with Open on Demand. If you're a fan of Internet Explorer 11 or something really ancient at this point in time, it will not work with this. It needs a modern browser. So make sure you have a modern browser when you're using Open on Demand. So at this point, the first activity we're going to have you all try to do is actually get on and into Open on Demand. So what you want to do is we recommend open your private browser incognito mode, so it makes it for easy log out when you're done. Basically, you want to point your browser at hps or mana.its.edu, and it will basically bring up the UH login screen, and you can log in. And then you should be presented with the screen that you see, much like this. So we'd like you all to go ahead and try this. If you do run into problems, you have problems connecting, it throws an error, speak up. Or, if you're having some other issues that, maybe your neighbors got in and you have a problem with the URL or something, you can ask your neighbor as well. When you all are done, please just, either speak up, or if you're on Zoom, you can put in chat that you completed, gotten on successfully as well.
This is the module. I just opening incognito, and then it gives you that you need to log in from Oh.
For now, get into the Open on Demand. So I'll step through, and then Olivia will actually go through for the Jupyter Lab part of it later. That's later in the presentation. So that's as far as you have to get, just logging in. Yeah. assuming by silence, I don't know, most people have gotten in, no problems. Okay, so logged in, you should have gotten the UH prompt like this. Log in with your UH credentials, and you're presented with this type of screen. So features of Open on Demand. So first thing it has is file thing. So file browsing allows you to basically represent your home on the cluster or your directories you have access to in a graphical interface. So instead of having to use the CD command, ls, and all things to navigate, it has a built-in here where you can navigate it through your web browser instead. It even has a text editor. So if you want to edit files in here, instead of learning something like Vim, Emacs, or Nano, you can edit here and save it, and it'll save it on the cluster for you as well, since you're editing files on the cluster. It has, as I said, file upload and download. Though with Open on Demand, we don't recommend large file transfers. It's not designed for that. So, anything larger than about 5 gigabytes, you probably do not want to use this interface for. You'd want to use one of the other modes of transfer, such as through the DTN nodes at that point. It has a capability to submit jobs to the cluster. We'll skip over this since we're not actually use it for this workshop, but just know that it has hooks into basically the scheduler. It can pull up an SSH shell, as we said. So if I were to click on this, it opens up an SSH shell on my home, and we can do the, if we did an ls here, we'd see the same representation we saw of my home through the web browser as well. Then finally, we have interactive apps, which, as I mentioned, we have a desktop one installed. We have Jupyter Lab, Jupyter Notebooks, and RStudio Server. So these interactive apps basically allow you to start up these resources or these applications on a compute node in the cluster, and then have those jobs proxied or not really pulled back out so you can view them through your browser here without having to use your resource on your local machine. So basically, it uses a compute node to basically run the service, and basically all you're doing is interacting through a thin client of your browser. Let's see what else was here. So that's what this is. Look at that. Oh, so along with the interactive apps, just going over this form of it. So the interactive apps basically give you a form to submit for what resource you need, but there's also this capability. So with a cluster and any resource where you have more users than actual resources that are available, it can take a while for jobs to begin. So it has the ability to basically email you when your session starts. So you can basically submit, walk away, maybe 12 hours later it starts, you'll get an email notification, and you can come back and use the resources at that point in time because your job is now started. So that's kind of nice to have that capability. So key points from this section basically are, SSH is a traditional way to connect to HPC systems, but alternatives like Open on Demand do exist to ease the access and simplify access to HPC systems. I guess any questions about, connectivity to clusters, how people typically have been using clusters to connecting to clusters, things like that. If not, I'll hand it off to my fellow presenter, Olivia, to basically walk us through Jupyter Lab and Open Demand, how we can do machine learning with GPUs and CPUs on Mana, as well as possibly touching on the file system, basically to go over things like that, what choices you should make. Take it away, Olivia.
Great. Thank you, David. Let's see. Let's share my screen. Okay, can you see the modules? Okay.
Yes.
So now we're moving into kind of like how we saw before, how to request computing resources on Mana. So if you haven't already, there's a Jupyter notebook that we're going to use throughout the rest of this workshop. So you'll right-click, save linked as, and make sure you save it as a notebook file, because we'll use that later. But now we're going to use this form that we saw earlier. So now that we've logged in and hopefully your screen looks like this, we're going to go into interactive apps and go into a Jupyter Lab. Load. Okay. And then we're going to request resources to use for this workshop. So it says in the modules here what we want to request, but we are going to request to work on the workshop partition. You can put however many hours, I would say at least 2, so we make it through the workshop. We're going to request 1 node, 1 task per node, 4 cores per task, 24 gigabytes of RAM, request 1 GPU and any GPU. So once you fill out these sections, you'll hit launch, and our request will be queued, and it should give us resources in a few minutes. So yeah, walk through the worksheet, lean on the people around you, or speak up if you have any questions. People in the Zoom, we can use the chat as well. Okay. Has everyone been able to see either queue or starting?
What were we supposed to put for the when we're starting the Jupyter Lab, the resources and stuff?
So the count should be blank. The partition should be workshop. Number of hours should be more than 2. 1 node, 1 task per node, 4 cores for that task. 24 gigs of RAM, 1 GPU, and then any type of GPU.
Sweet. And then hopefully eventually you'll see that it's running. But I'll talk about Jupyter a little bit before we keep going. So Jupyter, why use Jupyter? So most data scientists prefer Jupyter because it provides an interactive platform to store data, code, visualizations, equations, text, output all in one place. It gives users flexibility to analyze their work and streamline workflows. It also provides a collaborative workspace. You can easily share your work in different formats like JSONs, PDFs, and HTMLs. It supports several programming languages. You can use different versions of softwares. You can switch between different environments, and it has an interactive output. And you can easily run sections of code without impacting other sections. So what's the difference between a Jupyter Lab and a Jupyter Notebook? So what we downloaded is a Jupyter Notebook, and what we're working in is a Jupyter Lab. So a Jupyter Notebook only allows you to access 1 notebook in an environment, whereas Jupyter Lab gives a better user interface, and here you can work on notebook files, Python files, and you can have access to a file system. So a lab is basically like an extension to a notebook. So yeah, in the file system, you can upload, download files. You can work with multiple Jupyter notebooks and multiple environments all in the same window. And so how does it work? Your code is written in code chunks or cells, and the browser passes it through a kernel with your environment, so all your loaded packages and libraries to run the code, and it returns an output, which we'll see practice in these exercises. So hopefully by now everyone sees the Jupyter Lab running. Let me know if not. Let's see, this question. yeah, it has to be workshop. So the partition you're using, there's several other ones, but for this workshop, we're just going to be working in workshop. All right. So great. Module 3, we set up a Jupyter lab. Now we're going to practice installing modules and setting up an environment. So let's see. So in order to install softwares and modules, we need to use a package manager. And package managers are softwares already installed on the cluster, and we can use to install libraries and softwares and even choose which versions to install. And then using the following commands, we can see what modules are already available on the cluster, or which ones are already loaded, or which ones we want to load in our environment. So if we go back to our Jupyter lab and hit this link host, we'll get a command line prompt, and we want to say, yes, I want to continue connecting. So again, to get to the command line, you can hit this blue box here. We'll get a nice command line. So kind of demonstrating these commands, if you say module avail, we can see all the modules available on Mana, and there's lots to choose from. If we say module list, we see the modules that we have loaded, and right now there's none, but we'll do that eventually. And then, well, we'll get to that, but module load, that's the process of actually loading modules. So there's modules, and so what is an environment? When you're working on different applications or with different people on a project, there's many different versions of the same software or modules you can be working with. So by creating an isolated environment and storing libraries and their versions, we are creating sort of a directory of software we need for a specific project. And to create an environment, there are two popular tools. There's pip, which is a tool to install Python software packages only, and there's Anaconda, which you can also install Python packages, but it also allows you access to C, C++, and R packages as well. So for this workshop, we're going to focus on using Anaconda as our package manager. And this package manager analyzes the current packages and versions in your environment and then installs the packages you need. So this creates less errors when installing libraries, and you can install softwares written in any programming language. Okay, just checking the chat. Let's see. So, all right, so for our deep learning tutorial, we're going to start by setting up our own environment. So we're going to kind of all do this together. Feel free again to use the people around you, the chat, or speak up if you run into any errors. So we are going to set up our own environment. So the first thing we need to do, we're going to do this line by line. So we're going to load the Anaconda package as our package manager. So we're going to copy and paste these lines, module load, into this command line interface. And we hit enter. Nothing will pop up, but that should mean it loaded okay. Conda create. So we're going to create an environment and we're going to name it TF2, which is the abbreviation for TensorFlow, and we're using version 2. So I already have, since I've practiced this, I have an environment called TF2 already. So I'm going to call this workshop, but keep it TF2. So So conda create. And if it prompts you, you want to say yes to proceed. And you should get an output like this. So we've created it, and then the third thing we want to do is activate. So in order to activate our environment, we need to say source activate and the name of our environment. So TF2 say workshop. And we should see it's activated when there's
Olivia.
parentheses. Yeah.
Can you go back and show where you went to get the shell again? There's someone that's actually lost, doesn't know where to get the shell is. Why.
Yeah. So were you able to successfully run a Jupyter lab?
Yes.
Awesome. Okay, so you should see this kind of window here, and it should say host and this link here. This link should open up the command line. And if it asks you if you want to proceed, you'll say yes.
I think I closed it at page.
Close this page.
Yeah.
Okay, yeah, that's totally okay. I think
So you can reconnect to the session. So you have,
Mhm.
Let's see, you already connected. So then you can go back to the this. If you go back, you point your browser back at mana.its.hoi.edu. You can log back in if you
Okay.
go to the page, and then so you see next to Olivia's interactive apps, there's little boxes. If you click on that thing, you'll bring up your listing of all your interactive sessions that are currently for your session. And it should list the Jupyter Lab one.
Okay, I got it. Thank you.
Awesome. Yay. Okay. Yeah, little boxes should bring you back here. And then this link here brings us to the command line. Okay, how are other people doing? Have we activated an environment?
Yes.
So now I'm in the shell, and then what do I enter?
Yeah, so once you're in the shell, you're gonna start by, let's see, do you have access to this link, the modules?
No, not that I know of. Let's see.
I'll put a link in chat for it again.
Yeah, it'll be in the chat.
You go here.
I also put it in the chat. Okay, and then from that page, this is kind of where I'm sharing my screen as well. And so we're just going line by line, kind of copying and pasting each of these commands into the command line. And so first, you're loading Anaconda. So you'll copy paste and then hit enter for the command to run, and then you'll create the environment and activate it. Okay, so while you're doing that, it sounds like the people in person are good. So next we're going to install these packages into our, or libraries into our environment. So conda install, and then, let's see. Conda install all these packages, and this is going to take a moment, but you should see this sort of dash line spinning, which means it's working and installing the libraries. But if you get any errors, let me know. And eventually it's going to prompt you with, are you sure you want to install this? And you'll just say why or yes. And yeah, this will just take a moment, but yeah, after it asks you if you want to proceed, while we're waiting for it to install, we can, all right, here. So if it asks you to proceed, you want to say yes or why for it to keep going. But while we're waiting for it to install, we can take a break. And if you have any questions or run into any errors while these are installing, I'll be here. But we can, while this is downloading,
Olivia, I do have a question.
yeah.
When you're typing in yes or no, does case matter?
No, I don't believe it does in this case. In this case.
And actually, by
This does not
default,
matter.
it's going to do Y or yes. So if you hit enter, actually, at the proceed prompt, it'll just say yes by default.
Mhm. I think is that what the brackets mean? The default is, yeah. Great. Okay. So yeah, hopefully this is what you see at the end, but we'll take a quick bio break. And we'll continue with the sections at, let's say, 5:52. We'll do 5 minutes.
Case issue. So I had, I was reading capital and monthly, the lowercase.
I saw you online.
Oh yeah,
It's like,
I was like, how can I get complicated them? So I had it on my phone. Yeah.
nice. It's good for her.
Yeah. I don't think that's that.
Thank you.
Yeah.
So that now I saw but starting and have this one stop at the same time. That one start loading. That's afterwards, but well, most of the code that's also you keep really careful, right? So you keep it in your own cells, then you run. Yes, but there's some that really need to go. Get through all.
Alrighty, so we'll continue on. So now that we've set up our environment, hopefully was everyone able to install the packages okay? Take that as a yes. Let's see. Awesome. Okay, so we set up our environment. Jupyter can't quite see or access these packages because there's no interface for them to do so. So we create what's called a kernel. So Jupyter can actually use these modules. So to do that, we're going to install one more package. So we'll conda install IPY kernel. And we'll say yes to proceed. So same process, just one more. Okay, and hopefully that runs smoothly for everyone as well. And then since we have that package installed, we're going to create the kernel. So you'll have the environment TF2 so we can use it in our Jupyter lab. And you should get output that says something like installed the kernel. So just copying and pasting these two lines to create a kernel we can use in our Jupyter lab. Okay. So stop me if you run into any errors, but we'll keep going. And so now that we've set up the environment and created a kernel, now we're going to get into one of the things you can do with Mana. So machine learning or deep learning is a popular thing because of the GPU resources. So in this module, we're going to look at the performance of a GPU versus a CPU with a deep learning task and how we can use Mana to do machine learning. So for this tutorial, we are using the CFAR 10 dataset. And this is a common dataset used in machine learning and computer vision research. What we're using is a subset of 80 million tiny images, and this consists of 60,000 images. And the images are labeled with 10 different classes. So we see in this image, we have airplane, automobile, bird, cat, deer, dog, frog, horses, ship, and truck. So those are our 10 different classes and all sorts of images that go into them. And so each class has 5,000 training images and 1,000 test images. And each row represents a color image of 32 by 32 pixels with 3 color channels, so red, green, and blue. So this is the image data set we're working with. And whenever we create a machine learning algorithm, the basic workflow starts with collecting data, preprocessing data, defining a model, training the model, evaluating and testing the model, and looking at how we can improve our model. So before we start this tutorial, we're going to go back to Open on Demand, and now we're going to connect to Jupyter. So if you lost yourself and can't find this page, you're going to go back to Open on Demand, the home page, and you can click Zoom bar is here. These two sort of boxes, and you should find yourself at this page. And we're going to connect to Jupyter, so this bottom blue box. Okay, and then once we connect, we should see the kernels that we created. So you should see TF2. And then this is where we are going to upload that Jupyter notebook that we did in the third module. So let's see. I believe it's so this upload button, the line with an up arrow, you're going to upload your Jupyter notebook, which I think I called it Participants Copy 2022. So you'll double click on that. And it should upload. I actually already have it. And you'll double click on it on this left-hand side in your file system, and it should open for you in the main window. So is everyone able to upload the notebook okay? Great. Okay, and another thing you want to do as well is make sure next to this bug icon, you want to set the correct kernel. So we don't want to be in Python 3 because it doesn't have any of those libraries we just installed. We want to be in TF2, or I just called mine Workshop. But the tutorial has TF2. So you'll select that, and that should hopefully help us run this with all the correct libraries we want. Okay, let's see. So if we're all good, again, stop me or feel free to put in the chat or ask your neighbor if you have any or run into anything. But this first activity where you want to import all the relevant library. So I actually, all of the code blocks that are in the HTML, I put in the notebook, so you can just kind of follow along and run each of the cells. So in order to run a cell, you'll select the cell and see this sort of blue vertical line, and you'll hit the play button to run the cell. So here we're importing all of our libraries, and you should see an output like this that says successfully opened dynamic library. And so if you do get any errors, that might mean that you're not connected to the correct kernel, or there was something that happened when you installed libraries. So let's see. So how are we doing? Did we successfully import all the libraries? Okay. Okay, we'll keep going. So next we're checking to see if we're using a GPU or a CPU. So in this code block, we'll run it, and we should see that we found a GPU we're using, and we're also using a CPU. So we're using one of each. And so CPUs and GPUs can be used for machine learning tasks, but depending on factors like speed, power, and cost, one might be better to use than the other. And so we'll kind of see how they do with speed and processing power throughout this exercise. But so far we see we have one of each, which is a good sign. Next step is, once we have all the libraries, we want to load the data. So you should get an output like this, and this just shows that we have 5,000 images in our training data set and 1,000 images in our test data set. So we've kind of separated the two. We have a 32 by 32 pixel image, and we have 3 color channels, the red, green, and blue. And each of the images has one label, like the bird, frog, horse sort of deal. And we have 10 classes. So yeah, we've loaded the data. And then in this next cell, we're telling it what each of those classes are. So airplane, automobile, bird, and so on. So we'll run that block. No output should come out of this, hopefully. And then we want to see some examples of images. So we're going to plot a few, and these are kind of what the images look like, not the highest resolution, but we can see that these small images, we can see kind of the outline of a frog, a truck, a deer, an automobile, a ship. So these are just examples of the images we're feeding into the model for it to identify. Let's see, just checking in. We're able to run these okay so far. That's a good question. So we'll get into Keras and TensorFlow. So let's see. Keras is the interface that allows us to use to make machine learning models. So it's kind of an interface between TensorFlow and Python. But TensorFlow is the open source software used in machine learning to train neural networks. So TensorFlow is the software, and Keras is sort of the in-between that allows us to code in Python to build the models. And then H5 is a data file type or format, data file format for big files.
Sean just gave an explanation in chat.
Yeah. Great. Okay. And then actually, yeah, so HT5 files, that's what we're doing next. In this code chunk, we're converting the data set to an HTF5 file format. This is important for and useful for storing large heterogeneous data sets for quicker processing. So even though we have a subset of our giant image data set, this is still a good thing to do. And then this next chunk, we are defining the model we're going to train with. So this is a really complicated process for non and machine learning users. It's complicated under the hood, but kind of like explained before, TensorFlow is the open source software used in machine learning to train the neural networks, and then Keras is the interface between TensorFlow and Python we can use to build and train models. And so we are creating a sequential model with convolutional and max pooling layers. Oops. Let's see, is there... I just rearranged things.
Control Z should let you undo that.
Thanks. Perfect. So yeah, but since this is complicated, sequential just means we're building this thing layer by layer. Awesome. And then let's see, and it gives you, so your output, you'll kind of get this red block, but it also gives you a summary of the model as well. And then in this next block, we're creating functions to generate data. So this allows us to break up the image set we're working with into what are called batches, or just smaller forms of data to input into the model. And then in this next block, this is where we're generating batches for the training. So we're using those HDF5 files. We're using 250 images at a time to train the model. And we're using that data generator class to do that. So we'll run that block. Let's see, and then next we're compiling the model, so it will be built up layer by layer to train our image data set. And now we are going to start training the model. So with this code chunk, we're going to train the model using a CPU, and then we're going to do it with a GPU. So when you run this code block, you should see epoch 1 of 10 and sort of this arrow chugging along, and this is just showing kind of the images being run through the model. And it kind of counts down a time. Let's see. Okay, so we kind of see that each epoch, there's 10 of them. Each of them are taking about 45, 46 seconds. And so this, running through 10 of them might take some time. And so, let's see. So this is just showing the process of training, but for the sake of time to keep going, We're gonna Control C to kill this job. Let's see if it's or the stop button. That's right. And so keyboard interrupt, but this just shows that each epoch takes about 46 seconds using the CPU. And we want to do the same thing now with the GPU to compare the performance. So here actually I put new history, and so we're just going to call it history. That's one edit I need to make. We're going to run that. We're going to see the similar process of epoch 1 of 10. Should take a moment to start up. And we're going to compare the time and see how it does. So is everyone able to train the model and get up to this point if you're following along?
Yes.
Awesome. Keep getting an arrow. OS error in 11. OS. Unable to open.
Did you create the HDF5 file a few steps above? So at some point you have to make it and then.
Yeah, you can retry
Cell 6.
rerunning. Yeah, cell 6. This one that says convert data to HDF5. It should write that file. Wait, let us know what that does. Okay, so now already, if we're checking into the times, we're already through about halfway of our epochs, and it's taking 24 seconds per epoch. So with a GPU, we're seeing it take about like half the time it would for a CPU. So yeah, the GPU is noticeably quicker than the CPU because of its ability to handle large data sets and complex neural networks. So GPUs have the speed and the power, but can be costly. So that's why having an HPC like Mana with these shared resources is great to have when doing projects like this. So we'll let it run completely so we can complete the, or so we can do the rest of the blocks. How are the HDF5 files going? Candace.
Oh, I reset my kernel, so I'm just like rerunning all the cells to try to fix it.
Okay, cool, perfect. Okay, so it looks like it made it through all 10 epochs. So yeah, all of the layers took about 24 seconds. So we see, again, quicker with the GPU than the CPU. And so now we're going to plot the loss and accuracy for each of the data sets, so training and validation. And so for loss, we want loss to be as low as possible, and we want accuracy to be as high as possible. So the training model is in blue. It often does slightly better than the validation data set in orange. Just because the training data set, it sort of sees the answers or see what the image is being classified as, whereas the validation data set, it's sort of being tested on and not quite seeing what the image is being classified as. So, but they're doing very similar, same trends, which is good. And then the next cell should show us our loss and accuracy as a whole. So overall our loss is 0.79, which is kind of high, but that can be tweaked with some parameters. And then accuracy is 75%. And so with that, we can plot the predictions to see kind of what the model labeled these images as or predicted them to be. So the Y is the actual prediction labeled in the data set, and X is the prediction the model made. So it's doing pretty well. Like we see the cat is being predicted as a cat, ship is being predicted as a ship. In this case, airplane was predicted as a deer, automobile, truck. But for the most part, we see it's labeling correctly. And yeah, that just comes with more training. And yeah, every once in a while it labels something incorrectly. But yeah, that's kind of a process of deep learning using Jupyter Lab and using Mana resources. So let's see. Through all of this. So besides Mana, there are other free resources available to do machine learning. There's Google Colab, Azure Notebooks with Microsoft, Kaggle, and more information about these resources are also linked in the modules. So let's see, we'll keep going, or we can do the discussion. So either unmuting or speaking up, the discussion we have after going through this is, why do you think, or why would you need an HPC cluster over your personal computer? Or what other things could you use an HPC for?
You need it to run stuff faster than you can on your own computer.
You want to run something overnight or something and you don't want to leave your computer on?
Great, yeah, these are good examples.
You can do stuff in parallel.
Yep, you can do multiple things at once. Yeah, these resources kind of allow you to do all of those things, run things faster overnight, multiple things at once. So yeah, great. We'll keep going. So the last module for today, we're looking at file systems on Mana. And so we're gonna answer what a file system is, what is a distributed file system, and how do you optimize the file system on Mana. And there's a little exercise at the end, kind of building off the tutorial we just did using file systems. Okay. So what is a file system? The term file system is ubiquitous among operating systems. At some point in time, you might have had to format a USB flash drive, SD card, memory stick, and may have chosen between different file systems. And file systems are a way of operating systems to organize data, so documents, movies, music on storage devices. And from the storage device hardware perspective, data is represented as sequences of blocks of bytes. But that isn't really helpful or useful to regular users. So most of us really care about the file and where it's located, and we don't really think of things in terms of blocks of bytes. But luckily, the file system under the hood handles the organization and locating logic of these blocks of bytes for users, so you can run different commands and applications. So that's a file system. A distributed file system on the cluster like Mana, blocks of data that make up a single file are distributed among network attached storage or NAS devices. And the goal of a cluster file system is to organize and locate blocks of data, but across different networks, and present them to the end user as one contiguous file. The main benefit of stringing storage devices together in a network connected cluster is to increase storage capacity beyond what a single computer can have. So imagine having 100 terabytes of files on your laptop. The storage can be shared among different clusters, cluster users furthering increasing utilization of these storage devices. And so on Mana, there's two main supported file systems. There's a network file system and a file system called Lustre. And Mana users have two special folders called LustScratch and NFS Scratch, where they can temporarily store data on the cluster. And something to note with these folders is that data within them will be purged after a period of time, so it's important to save files that are important in your home directory. So for this first exercise, we're going to locate both of these folders in our Jupyter Lab notebook. So if you keep scrolling beyond our deep learning tutorial, you'll see the commands here for these exercises. So we want to run these cells. So this first one, you're just locating your home directory, and this is where you want to be so you can see the file system folders. And then we are going to see, so ls just shows everything within your home directory. So I've got a lot going on here, but you should find LustScratch is a folder in your home directory on Mana, and NFS Scratch is another folder. And these exclamation marks are sort of a magic symbol that allow us to execute Linux commands in Jupyter. So is everyone able to find these two folders in their home directory? Sweet, I see some thumbs up. All right, so those are the two file systems on Mana. So the Lustre file system is a parallel distributed file system. This is where file operations are distributed across multiple file system servers. So in this image, we sort of see all of the systems. And in Lustre, storage is divided among multiple servers, allowing for ease of scalability and fault tolerance. The file system is great for high speed read and write performance, which is something we're going to test later on in this module. So Lustre file system, files are distributed among multiple file servers, whereas in the NFS file system, this one is a single server distributed file system where file operations are not parallel across servers, but a single server serves requests to the cluster. So this one we saw these clients connected to multiple networks. This one we're just connected to one. NFS is an older technology and has the advantage of having gone through the test of time and is a trusted among cluster architects. So how do we know we're choosing the right file system? Depending on the user's needs, different file systems are optimized for different purposes. One may be optimized for random access speed, one with error correcting capability, one with high redundancy to prevent data loss. So for this workshop, we'll focus on disk random access speed on the Mana cluster. And so on Mana, we have 3 locations for file storage. There's the home user, there's less scratch, and NFS scratch folders available to us, which we saw in the first exercise. And for the best performance, the read-write speed, we will want to use the less scratch folder. And we're going to do an exercise to compare the different read and write speeds. But yeah, as discussed above, the reason it performs better is because the Lustre file system is distributed across multiple servers, where the NFS is a single server system. Okay. So another thing we can do in this exercise is to check our usage in each of the folders. So if we run this block, you can kind of check into how much data you've used in each of the folders. So like in my home directory, I've used almost 50%, whereas in these folders, maybe because data's been purged, I've used less. But there's a lot of room in these folders and the scratch folders. So yeah, the command usage allows you to see what you used and what's available in each of these folders on Mana. Let's see. So any questions so far on file systems? Okay, we'll keep going. So now we're going to compare the read and write speeds in the 2 file systems. So we want to run this block. This one is just creating a function to write files and read files into the different folders or file systems. And okay. And yeah, again, all of this code is in the modules and it's in the Jupyter notebook. So now we're going to write a file into our less scratch and we're going to time it. This double $sign and time allows you to time a task. And so we see when we write into the Lustre folder, it only took us less than 2 seconds. And then to read, it took 83 milliseconds. And then when we do the same task in the NFS scratch, let's see, when we're writing to that folder, it will take longer. So we'll see how much longer it takes. So it definitely does take longer to write to the NFS. Let's see. Good count. So yeah, we clearly see it takes longer to write to the NFS file system rather than the Lustre file system. Actually, when situations. So there's a question when yeah.
The purge actually occurs right now every 25 days based on file modified time. So no, your files shouldn't be deleted while you're still running an experiment. That's you're writing to those files. So
yeah. Okay, so yeah, that's kind of the difference. So overall, we see the Lustre file system is faster than working from your home directory or the NFS file system. And so we can also use the Lust Scratch folder to optimize our deep learning code. So what we did in the previous module, we can do the same thing in the working from the Lust Scratch directory to speed things up, kind of like how we did with the GPU. So here, let's see. So here we're converting again to the HDF5 files, and we're working in the Lust Scratch directory. So give it a second to do that. Okay, looks good. And then we want to update the path to our data generator so that it's also in Lust Scratch. And we want to rerun our model. And so hopefully we'll see that the speed of our model improves working in the Lust Scratch, so the multiple server. Let's see. So yeah, we see it takes about 24 seconds, which is very similar to working with the GPU. Let's see. So yeah, you can see. So overall, file systems are ways operating systems organize data on storage devices. Distributed file systems organize data across network attached storage devices, so the NAS. Distributed file systems have the advantage of supporting larger scale storage capacity. Mana has two file systems. It has the Lustre and the NFS file systems. Lustre on Mana is set up with solid state drives, while NFS on Mana is set up with spinning drives or hard disk. And we see overall that the Lustre file system read has faster performance when reading and writing to files. So yeah, that's pretty much it for our HPC workshop. We'll take any questions or if you got stuck any point along the way. But I believe what's next is this assessment. So if you click on, if you're working in the modules, there's a Google form that you have time to fill out for the participants is here in this first part. But yeah, if there's any questions, let us know. But thank you for coming to our workshop on the HPC. And hopefully you can use Mana in things that you're working on.